Hi everyone. So this is just going to be a problem solving session, like I said earlier, but if you have any questions about the sample test, then we can go over those. Or if you have any questions, about topics in general, then we can solve more problems, about that topic. So you can say on mic or in the chat what you'd like to do. Okay, number 13, I'm gonna go look for it 1 second. Okay, so for this one, I think what you're supposed to do is calculate the mass fraction of CHNO, so you can get the grams of CHNO in aspirin. So to do that, we can so to get grams of carbon, what we have to do is do the mass fraction times grams of CO2 that we have. So how do we, calculate the mass fraction? It's just like doing the percent of everything. So to do that, we just take carbon out of the total, which is going to be 12.01 plus 2 times about 16 from the oxygen. And then we multiply this whole thing by the grams of CO2. And I think we have 2.20 grams. Okay, so from there, we can calculate how many grams of just carbon we have. If you put that in a calculator, you should get I think you get around 0.6 grams carbon. And then we can find how much hydrogen we have from the water. So we do the exact same thing, except we do mass fraction of hydrogen in water. And how do we do that? We take however much oxygen there was. So it would be like 2 times 1.08 divided by the total, which is 2 times 1.08 plus 16. And then this whole thing times 0.400 grams of water. And that gives us, if we calculate it, we should get around 0.04476, so we can just round to 0.0448 grams hydrogen. And then the amount of oxygen, we can just get that from we have 1.0 grams. So we just take 1.0 and we subtract from that 0.600 and then again 0.0448. And that's going to give us how much oxygen we have, because we started with the tablet that had 1.0 grams. And so if we calculate that, we should get 0.335 grams of oxygen. Okay, so then I think from here we can kind of do what we've been doing with the tables and everything, and taking so finding the ratios. So well, first of all, can we keep this in grams, or should we convert to moles if we want to find the formula? Right, moles. So how do we convert everything to moles? Right, so we just divide by the molar mass. So we can find that on the periodic table, and we get moles in the end. So if we divide this, we should get around 0.05 moles carbon. And then we take our hydrogen and do this exact same thing. And then we get, I think around 0.0444 moles. And then lastly, for the oxygen, we divide by around 16 grams per mole, and we get 0.0222 moles oxygen. Okay, so from here, how can we find our formula, our empirical, or our empirical formula? So what number should we divide all of these by? Yeah, the smallest one. And which one is the smallest one in this case? It would be, would it be the one for C, H, or O? It would be for O. So divide everything by that. I'll just put an arrow instead, so it's not equal. 2, 2, 2. And if we calculate that, this is going to be 1 for sure, and this is probably going to be 2. And this is going to be around, looks like 2.25-ish. But since this isn't a whole number, what we want to do is multiply. Well, so if we just keep it like this, then we're going to get something like what that looks like this. 2 and then 0.1, but that doesn't really make sense, right? This isn't going to work out. So what should we do to make this a whole number? Like what should we multiply by? Let me say we should multiply by 1. Oh, okay, cool. We should multiply by 4. Perfect, but we can't just multiply this by 4. We have to make everything equal, so we multiply all of these by 4. And if we do that, we should get C9H8O4. And so this is going to be our molecular, or not our molecular formula, it's going to be our empirical formula. But since it tells us that the molar mass is between 170 and 190, if we calculate the molar mass of this, it should be around that. So we find that this is actually the correct formula. So the empirical and the molecular formula are actually the same. So this is our answer. So I think that would be B. So that's how we would do something like that. Are there any other questions? Okay, sure. Okay, so for number 29, what we have to do is, well, so first of all, we're already given the equation, so we don't have to worry about writing that out. And so for here, it tells us assume 100% conversion. Okay, so what should we do? Well, let's start out with what we're given, which is 5.0 times 10 to the 13 grams of aluminum. And what it's asking for is this thing, bauxite ore or whatever. So how can we get to bauxite from aluminum? So first of all, okay, so it tells us 50% Al2O3 by mass. So if we can find how much Al2O3 there is, then we should be able to get bauxite. So what's our first step? Do we want it to be in grams, or should we convert to something else? Right, moles. So we can convert to moles just by using molar mass, and that's around 26.98 grams. Okay, then. From here, since it tells us this bauxite ore or whatever contains 50% Al2O3, we notice that it's right here, right? So we use the formula to get some sort of ratio. So what ratio do we need? Well, how many moles Al2O3 for however many moles Al. So what should we put on the top and what should we put on the bottom? Okay, well, I think that might be the next step, but the first thing we have to do is just look at the molar ratio. So we can get that from the equation. So we just read off the coefficients. Right, so on top would be 2, and then on the bottom would be like right there. So what would go on the bottom there? Would it be a 3? Would it be a 3? Yeah, it would be a 4. Perfect. And that's just from reading the equation. We just read off the coefficient of whatever we need. Okay, so now we have it in moles Al2O3. This is kind of, I'm gonna make it smaller, sorry. Okay, I'll just change the color. Okay, so from here, what we want to do is, let's see. I think we're given, so in 1 mole Al2O3, how many grams are there? Let's see, I think it's around, calculate it. Okay, I think it's around 149.96 grams. You can correct me if I'm wrong. And then from here, the last step we need to take is we're told that 50% of bauxite ore is Al2O3. So what does that mean? That means for every 1 gram of bauxite ore, we have 0.5 grams of Al2O3. Oh, so I got the 149.96 from calculating the molar mass of Al2O3. So I'm pretty sure that's right, but I'll check again. Okay, I think I did it wrong. I think it's around 101 or something like that. I'll just write out I'll just put molar mass. This is the molar mass. Yeah, I think that's right. So then from there, if we calculate this whole thing, then we should get around 1.9 times 10 to the 14. So the answer we should get is C. Oh, right. I forgot it said that there. Thank you. Okay, and then for the next one, number 30, let's see. For the reaction, what mass must be consumed? okay, so it gives us all this information. So we're given the equation. So we're told 3.71 times 10 to the 23 molecules of H2O are consumed. So first of all, this equation doesn't tell us the molecular ratios or anything. It tells us the molar ratios, right? So if we want to use this as kind of a bridge to get to however many, grams of P4O10 are consumed, then we want to be in moles. So how do we convert this big number into moles? So what's our conversion factor? So if anyone knows the answer, you can, yeah, Avogadro's number. So does anyone know the number off the top of their head? You can type in chat. 6.0, oops, it's around 6.022 times 10 to the 23. Okay, so let's convert to moles of, what do we start with? Water. So then we get around 0.616 moles of water. Okay, so now from the moles, we can calculate however many grams of P4O10 we need. I think, yeah, this looks all right. So then moles. So what ratio are we going to use here if we're dealing with this and this? So what number should go on the top and what number should go on the bottom? And anyone can answer this? Yeah, so 1 goes here and then 6 goes there. And then we want our end results to be in grams. So in 1 mole P4O10 tells us this many grams, 283.89 grams P4O10. And then so our answer is going to be in grams. All right, if we calculate this, we should get around 29.1. So I think that one should be B for 30. So that's how you do that one. Okay. Are there any other questions? No worries. All right, 33. Okay, so when 20 grams this and 60 grams O2 react to form CO2 and water, how many grams of water are formed? Okay, so I think for this one, it doesn't give us the equation, so we have to think about, what our equation would be. So C2H6 plus O2 gives us, what the heck? Gives us CO2 and water. So that's what it tells us, right? We put in this much of this and we get CO2 and water. So if you're given, just a chemical equation, we should always make sure first to see if it's balanced. So right now in this state, do you think it's balanced? Yeah, no, for sure not, right? Yeah, so how would we balance something like this? So like what should go here? What should go here? What should go here? Oh, that's not that great. D and E. Yeah, perfect. So this should be This should be a 2, this should be a 7, this should be a 4, and this should be a 6. So if we do that, we have, 14 O's and then 4 C's and then 12 H's on both sides. Okay, that looks good. So from here, we're given grams, C2H6, and we should probably convert this to moles. So how do we do that? We just, divide by the molar mass, or in this case, divide by the molar mass. So 1 mole C2H6, and tells us molar mass. Okay, it doesn't tell us molar mass, so we have to calculate it. It is around 30.068 grams. Okay, then. And next, let's just, leave it like that. We're going to find that gives us around 0.665 moles C2H6. Okay. And then, what do we want to do? Okay, so 60.0 grams O2, and we do the exact same thing. So divide by 32. That's going to give us around 1.875 moles O2. Okay, so from here we want to find the limiting reactant, right? So which one is the limiting reactant? How do we find that? Well, last time I showed you a shortcut. So all we have to do is divide by the coefficient, right? And whichever one is smaller is going to be our limiting reactant because it's what's used up first. So let's compare 0.662 divided by 2 with 1.875 divided by 7. So if you do that, which one is smaller? Is it greater than or less than? Divided by 7. So this is greater than. So if we know that this one is for C2H6, this one is for O2. So if we know that this one is bigger than this one, which one is going to be the limiting reactant? The smaller one. So this is the limiting reactant. Okay, so now that we know that, all we have to do is take this and use it for our calculations. So let's see, 1.875 moles O2. And we're trying to find grams of water, so we just write out our ratio again. So moles water and then moles O2. So from the equation, we know 6 goes on the top, 7 goes on the bottom. Just reading off. And then if we do that, or well, let's write out everything. So now that we have it in moles H2O, how many grams are there in 1 mole of water? It looks like around 18. So then we should get around, I think around 28.9, around like 30-ish. Is that right? Yeah, 30-ish. So So it wouldn't be any of these. It would be E, none of these. So that's how you do something like 33. Are there any other questions? Okay, 39. Okay, so here we're told what the percent yield is, and it's asking us what's the actual mass that's produced. Okay. All right, so again, we're given the equation. And we're also given grams nitrogen and then grams hydrogen. Okay, so first let's try to convert everything to moles so we're more comfortable with everything. So grams nitrogen, let's convert that to moles just by using the molar mass, and that's around 28-ish grams. That gives us 0.7697, I'll just say 0.77 moles N2. And then what else? 4.45 grams of hydrogen. Okay, cool. So let's convert this to moles. It's around 2.016. And then 4.45. Okay, that's what I get from putting it in the calculator. All right, so this is how much is reacted with, but let's calculate how much is actually, required for this amount. So how much would that be? It would just be, okay, so 0.913. Well, no, okay. So first, let's look for which one is the limiting reactant. Sorry, it's kind of getting all over the place, but first let's just find which one is the limiting reactant. So how do we do that? Again, we just want to divide by our coefficients. So in this case, it's dividing by 1, so it stays the same. In this case, we're dividing by 2. So, well, we're going to get a number that's over 1. So this is going to be our limiting reactant. And next, now that we know that, 0.913 moles N2. So we're told that the percent yield for this reaction is 82%. So what does that mean? So that means here, so for 1 mole N2H4, 1 mole N2, if we used everything up, then we would produce 0.913 moles N2H4. So this is in kind of the best case scenario. But if we're given a percent yield, that means we should multiply by that, 0.82 times 913. Or let's just assume that, yeah, okay, so if we do that, we should get around 0.75-ish. And this is how much we actually get. Because that's how we have a percent yield in this case. And so from here, this is asking us, what's the actual mass of hydrazine produced, then all we have to do is convert this into grams. And we know the molar mass is around 32. So if we just multiply, we get around 24. So I think our answer should be, in this case, it should be B. And yeah, so the reason we multiplied by 0.82 in this case is because it tells us the percent yield. The percent yield is just telling us, if this is however much, is produced in the best case scenario, only 82% of that is produced. So only, 80% of that is yielded. So that's how you do something like that. Let me know if that doesn't really make sense and I can do some more problems like that. And are there any other questions? Okay, sure. Okay, so for this one, we're starting out with some dry O2, which we're told occupied 143 milliliters at STP. So we're told at STP, so what number should we think of? Like what's kind of the golden number STP? Yeah, 22.4 liters. So for 1 mole of anything, it's going to be 22.4 liters. So knowing that, we can go ahead and convert 143 milliliters. Well, let's just convert this to liters first. So it's just going to be 0.143 liters. Why is that? It's because 143 milliliters, there's going to be 10 cubed milliliters per liter. So I just move it 3 times and we get 0.143 liters. And then next, what we should do is convert this into moles. How do we do that? We use this right here. And that's because it's at STP. So if we do that, we get around 0.006384 moles. And then using this, so it gives us this formula. So this just tells us the ratio that we need. So if we have this many moles of O2, let's copy this. What's the ratio we need to multiply by to get into moles of KClO3? So I would go here and I'll go here. Right, perfect. So 2 goes here and then 3 goes there. And if we do that, we should get around 0.004256 moles KClO3, because this cancels. All right, cool. So then we can find the mass of KClO3 that's produced. So how should we okay, I should have done this in one step. We can just 1 mole KClO3 is, it tells us 122.55 grams. And that should give us 0.522 grams KClO3. All right, great. So now for our last step, it's asking us what percent of the original mixture was KClO3. So out of the total, which is 1.34, we had 0.522 grams of KClO3. So how should we find the percentage? We just take 0.522 divided by 1.34, and then we multiply by 100%. And then we get, oops, around 38.9%. So I think our answer for 56 should be A. So hopefully that one makes sense now. Are there any other questions? Or if there's anything confusing, then you can just stop me and let me know. Okay, determine the coefficient for O2 when the following equation is balanced in standard form. All right, so this one is asking us to balance this. So if you have something like this where it has C, or it has carbon, hydrogen, oxygen, and everything, I think this is combustion, right? Anyway, so do you know the order we should do this in? Like, what should we balance first? Like, did you learn in class about the order? Yeah, so you want to balance C first, then H, and then O. So knowing that, let's try to balance C first and see if this works out. So let's put an 8 there, right? And then let's try to do the H's. So there's 18 on this side. To match that, we should put 9 there. And now we just have to do the O's. So there are 16 and then 9, that's 25. So let's put 25 over 2 there. And then this works, I think. We just have to multiply everything by 2. So then we get 2 CH18. I'm not going to write the states. O2, and then 16 CO2, 18 H2O. So I think the answer to 25 or 22 should be D. So does that make sense?
Yeah.
Okay, cool. Are there any other questions? 19, okay, sure. Okay, so for this one, I think this is really similar to another problem we did, I'm pretty sure. But pretty much what we want to do is, so we're told this only contains carbon, hydrogen, and oxygen, and it's burning oxygen and it gives us this much CO2, this much H2O. So basically to find, this is pretty much telling us that all the carbon in this compound went to the CO2 and all the hydrogen went to the H2O. So knowing that, we just have to take 0.9267 grams and then multiply it by the mole fraction, which is, how much carbon there is in CO2. So how do we find that? We just do 12.01 grams per mole, and then here is 12.01 plus 2 times 16 grams per mole. So this is just telling us there's this much carbon for every thing of carbon dioxide. So if we multiply, we should get around 0.253 grams of carbon. So all the carbon came from the CO2. So all the hydrogen should come from the H2O. So what do we have? We have 0.1897 grams. We can multiply this by mole fraction. So how much hydrogen for everything of water? So 2 times 1.08 grams per mole. And then the molar mass of hydrogen, or H2O, which is just plus 16-ish grams per mole. And that's going to give us 0.0212 grams hydrogen. And so where did the oxygen come from? Well, it's just whatever is left over, right? Since, what you started with is what you end up with. So out of the total, we subtract what we just found, 0.253, 0.0212. So if from the total, which is made up of all, CH and O, we subtract all the carbon, we subtract all the hydrogen, we're going to be left with however much oxygen we have. So minus 0.0212 should give us around 0.2245. All right, so now what we have to do is convert everything into moles. So we can do that by, just dividing by the molar mass. Divide by the molar mass, divide by the molar mass, divide by the molar mass. And for carbon, we get so for carbon, we get 0.0211 moles carbon. Hydrogen, we get I'll write out the molar mass just in case. Okay, so for hydrogen, we have 0.021-ish. And then for oxygen, we have around 0.014-ish. Okay, so what number should we divide all three of these by to get the empirical formula? Yeah, right, so 0.014. So then divide this by 0.014. All right, this is about 1.5. This is also about 1.5, and this is just going to be 1. So let's combine everything. We get C 1.5, H 1.5, and then O. So yeah, we can totally use the chart thing with this. I just wrote like this because I didn't have too much room, but if you have room, then go ahead and use the chart. And then now we have this. So can we just leave it like this, or is there something we should do to everything to make it a whole number? And if there is, what should we multiply everything by to get a whole number? Yeah, 2. So let's multiply all of these by 2. And we get around, or we just get C3H3O2. And yep, that's an option. It's C. So the answer to 19 should be C. Yeah, hopefully that makes sense. Are there any other questions? Okay, so number 18, it tells us the vitamin C contains CHNO, and it tells us the mass percent of C and H, and we can figure out O from that. So what's the percentage of O if we're given C and H? So it all should add up to 100%, right? So 100 minus 40.9 minus 4.58. And we know this because it tells us vitamin C contains just CHNO. So if we do that, we get 54.52% O. So that's the percentage of oxygen in vitamin C. And now it's just as simple as doing one of these problems. So what we do is, let's just assume we have 100 grams of vitamin C. That's just so that our numbers are a lot easier. So let's say we have 100 grams of vitamin C, then how many grams of carbon do we have, and how many grams of hydrogen do we have? How many grams of oxygen do we have? So yeah, right, so 40.9 grams carbon. Yeah, just the same as the percentage. So 4.58 grams hydrogen, and then 54.52 grams of oxygen. All right, cool. And then from here, now that we have all the grams, what we should do is convert everything into moles, and we can do that just using the molar mass. So let's divide this by the molar mass. Divide this by the molar mass. Divide this by molar mass. And I'll move this up here so I have a little more room. And then we get 3.4055 moles. And then we get 4.544 moles hydrogen. Then for the last one, we get 3.4075 moles oxygen. Okay, so what number should we divide all these three by to get our empirical formula? So which number is the smallest out of these three? Oh, okay. Yeah, so it would be 3.4055. So this is about 1, or that's exactly 1. This is about 1. This one is going to give us, okay, it's around 1.33. So to make this a whole number, what should we do? Or at least about a whole number. Multiply by 3. Yeah, perfect. So let's multiply this by 3, multiply this by 3, and multiply this by 3. So if we combine everything, all right, to the side, we get C3H4, and then O3. Okay, cool. And then it tells us that the molar mass is around 180 grams. So then let's calculate the molar mass of this first. Okay, so very roughly, it's about 90 grams per mole. So knowing that the molar mass, the molecular formula is around 180, what can we do to this to make it 180? So if one of these is 90 grams per mole, how many of these things do we need to get 180? Yeah, 2 of them. So all we have to do is multiply everything by 2, and we get C6H8O6. So the answer for 18 should be D. So yeah, hopefully that will make sense. Are there any other questions? Okay, 24. All right, so this one is asking us to balance this thing. So if you balance something that has these polyatomic ions, just think of them as one big chunk. So you should always start by doing the most complicated ones first. So let's try balancing SO4 first. So yeah, I think that would be a good way to go. So, okay, so if we have 3 on this side, we need 3 on this side. What should be in front of the CaSO4? So if we have 3 on this side and we need 3 on this side, what should we multiply by? To have the same amount of sulfate ions, would it be A1? So what should go in here? 1, 2, 3, 4. Yay, 3. So 3 goes in there. And then we know that we have the right amount of SO4 ions on both sides. So what's the next thing we should do? Well, why don't we take care of the calcium, right? So if we have 3 on this side, what should go right here?
Sorry, how'd you get 3?
How'd I get 3?
Yeah.
So I'm trying to balance the SO4, okay? And I know there are 3 on this side, so there should be 3 on this side too. So that's why there's a 3 in the front. And then, yeah, so the next step, we know we have 3 Ca on this side. So how many Ca do we need on this side? Another 3. So what goes in here?
3.
Yeah, 3, perfect. Okay, so now we can think of either, oh wait, this is wrong. All right, now we can either, it doesn't really matter what we do next because either way we're gonna get the same answer, but what should go in this last square here? We know there's, yeah, it should just be a 2, right? And if you check to see if it works, it does work because there's 6 OH, 6 OH, 3 SO4, 3 SO4, 2 Al, 2 Al, and 3 Ca, 3 Ca. All right, so now it's just asking what's the sum of the coefficients. So we just add up everything. 3 plus 2 plus 3 plus 1, and we get 9. So I think the answer is B to number 24. Yeah. Does that make sense? I'm not sure, but I can ask my dad later, and then I can try to let you know. Or I can ask him to send it to the chat or something. No problem. Are you guys confident in like balancing everything? Oh yeah, sure. Number 35. All right, so it tells us a chemical reaction has the equation 2A plus B goes to C. So in which case is B the limiting reactant? All right, let's just look at the pictures and see which one makes sense. So let's count out how many A's there are and how many B's and how many C's, or just how many B's. Okay, so how many A's are here and how many B's are here? How many A's are here? How many B's are here? How many A's are here? How many B's are here? How many A's here? How many B's are here? So just like count them. Okay, Roy, how many A's are in box 1 and how many B's are in box 1? Mm-hmm. Oh, wow. Okay. Thank you, Claire. So that's perfect. 6, 11, 5. Here it's 6 and 4. Here again, 6 and 3. I think that's right. Yeah. Looks good. Okay. So it's asking in which case is B the limiting reactant. So let's go ahead and divide. So remember how I said you should divide by coefficient to see which one is the limiting reactant? And so it's asking in which case B is the limiting reactant. So all we have to do is divide for everything that has an A, we just divide it by 2. And then we compare it to B. Wait, hold on. Is this right? I don't
Wait,
think
is the
so.
answer D?
No, I think the answer, no, the answer is B. So for this, just, all right, so think about it like this, okay? So if we use up all of the B and, okay, let's say we use up 6 moles of B. How many moles of A are we gonna need? We're gonna need twice as much. So we would need 12 moles of A, okay? In this case, we need 10 moles of A to react with 5 moles of B. In this case, we would need A moles A. In this case, we would need 6 moles of A. Okay, so in which case do we have some A left over? In case 2, right? Because we started with 11, we use up 10, we have 1 left. In all these other cases, A is used up first. So B has to be the limiting reactant in case 2. Does that make sense? All right, sounds good. Are there any other questions? Okay, so for this one, all right, so do you guys know about the law of conservation of mass? Conservation of mass.
Wait, did we learn this?
I'm not sure. Did you guys learn it in class?
I don't think we learned it.
Okay, well, have you ever heard of, how matter is neither, what is it? Neither created nor destroyed or something? No?
Yeah.
Yeah? Okay. Well, this is kind of one of the biggest things you learn in chemistry. That's why it's a whole law. There's a whole law about it. So all it's saying is what you start with, you end up with, okay? So if we start with this much and we end up with this much, and it's asking us the mass of oxygen reacted. So basically, all we're told is we start out with 3.869 grams of this mixture, and then somehow we form this many grams of Fe2O3. So we have more mass at the end than when we begin. So where could it have come from, right? So basically, it comes from the atmosphere, the oxygen in the atmosphere, and that's what it's asking about. So all this is asking is, what changed? So 4.141 minus 3.869 is going to give us some number. Zero 0.272 grams. And so the mass of oxygen reacted is just 0.272 grams. Because it's the oxygen from the atmosphere that reacts with the mixture to create Fe2O3, and that's where this jump comes from 3 point whatever to 4 point whatever. Does that make sense? Yeah, this one's pretty simple if you, as long as you know the law of conservation of mass. Are there any other questions? Is 44D? I'm not sure, I'll check. 44 is, okay. So for 44, which contains the largest number of molecules? Okay, and it gives us these different gases. So yeah, I think this one would be D. Number of molecules is going to be the same because we have identical 1 liter gas or 1 liter flasks, which means we have the same number of moles of each thing, so we have the same number of molecules. And it's 48C. I'll check. Argon has a density of blah. Okay, how many have a gal greater than that of argon? I have to do it, but I'll check really quickly. Let me just try calculating this at STP. Okay. Okay, yeah, I think number 48 would be C. That sounds good. Yep. And basically how you do this is you check, how many of these have a molar mass. Oh my God, have a molar mass that's heavier than argon. And then from there you can narrow down your answers. 37, sure. Okay, equal masses, H2 and O2 are reacted to form water. Which substance is limiting? All right, so let's just try writing out the equation. So we're told H2 and O2 form water. So can we balance this maybe? So yeah, what should go here, what should go here, and what should go here? T1, the H2O, and then 2 here. Oh, that's great. Okay, so we're told equal masses of H2 and O2 are reacted. So not equal number of moles, but equal masses. So if we convert that to moles, let's say there are X grams of whatever, H2 and O2. Let's divide by the molar mass. Let's do it for H first. And it's just some number divided by 2.016. And then for O, O2, H2, it's just some number divided by the molar mass, which is just 2 times 16. So it's just some number divided by around 32. So out of these two, which one is bigger? Right, H2 is going to be bigger because we're dividing by a smaller number. But we can't only compare the number of moles. We have to also remember that trick with finding the limiting reactant. All you have to do is divide by coefficient and see which one is bigger. So this one's going to stay the same because we're dividing by 1. Here, let's divide by 2. We get some number divided by around 4 point whatever. So still, if we compare these two, which one is going to be smaller? So yeah, which one would be the smaller one? Yeah, right. So O2 would be the smaller one because we're dividing by this bigger number. So then we found the limiting reactant. It's just going to be the smaller number after we divide by the coefficient. And so I think the answer here should be A. So hopefully that makes sense. Oh, and number 28. Okay. All right, so iron is produced from its ore by this reaction. And it's asking how many moles of O2 are needed to produce 4.6 moles of Fe. Okay. So we start out with 4.6 moles Fe. And then from here, so we're just given these two equations so we can convert from whatever we need to the mole O2, because just from this equation, we can't convert from Fe to O2 because O2 isn't even in this equation. So we just have to use this other equation to get the right ratios. So we're starting with Fe and we want to end up with O2. Okay, so let's try to write it out. So what is there in common between these two equations? Is it A, C, B, O2, CO, D, CO2? So yeah, what is there in common between these two equations?
C.
So there's CO in both of them, so that's going to be our conversion factor, okay? So looking at this bottom equation, what should go on the top here and what should go on the bottom here? Right, so 3 goes on the top and then 2 goes on the bottom. And then, well, now we have it in moles CO. So which equation should we use to convert to moles of O2? Should we use this one or this one? Yeah, the first one. So which should go on the top here and which should go on the bottom here? Yeah, perfect. So 1 goes on the top and then 2 goes on the bottom. How do we know that? We just read it from the equation. And so now we just multiply everything out and we get around, it's 3.45, which we can round to 3.5 moles O2. So we would choose B for number 28. Yeah, so it would be B. Does that make sense? Does this one make sense, Roy? Okay, cool. Are there any other questions? Okay, let's do number 40. Okay, so it says nitric oxide is made from oxidation of NH3 and its reaction is represented by this equation. I'm gonna go ahead and get rid of this. Okay. So an 8.7 gram sample of NH3 gives that. Okay. All right, so given grams of NH3 and we're given grams of NO and we're trying to find the percent yield of NO. Okay, well, first of all, do you guys know what percent yield is? Or did you learn it in class? Yeah, okay, cool. So first, let's go and convert our 8.7 grams NH3 to moles of NH3. So the molar mass of NH3 is given as 17.03 grams for every mole, and that gives us around 0.511 moles of NH3. All right, so actually let's write it all out in one big thing so it's easier. So for every 1 mole, or not 1 mole, for every 4 moles NH3, we produce 4 moles of NO. And so from here, we find one more step. Let's convert moles into grams. 30.01, that's 30.01 grams NO. All right, so what we calculated here is the theoretical yield Does that make sense? Because we start with what we're given and we calculate, the theoretical yield. So basically, what would we get if we used up all of this 8.7 grams of NH3? So let's calculate this big thing, and we should, this is just 1. So we just multiply 8.7 by 30.0 and divide by 17.03 when we get around 15.331 grams of NO. So what is the percent yield again? How do we find it? Is it the actual yield over the theoretical yield? Is it the theoretical yield over the actual yield? What is it? And this here is our actual yield. Yeah, right. So it would be the actual yield over our theoretical yield. So what do we get? We get just 12.0 divided by 15.331, which we found here, then multiply by 100%, and we get around 78%. So our answer should be D for number 40. Yeah, so hopefully that one makes sense. Just make sure you remember it's the actual yield over the theoretical yield, and the actual yield is given in the problem here. And all you have to do is calculate the theoretical yield. Okay. Does that make sense? Kenneth?
Yeah.
Okay, cool. Are there any other questions? If there are no more questions, are there any other topics you guys want to go over before time runs out?
Can you explain what actual and theoretical is?
Yeah, sure. So the theoretical yield is just what we get when we use up all of this stuff, right? So all of whatever is given in the problem. But the actual yield is how much is actually produced. So notice here, when we did this problem, if we had 8.7 grams of NH3, using all of it up in the best possible scenario, we would get this many grams of NO. So that's called our theoretical yield. So in theory, we should get this much. But in labs and stuff, that doesn't always happen. Things can get like lost along the way, depending on what your setup is like. So it tells us that our actual yield is just 12.0 grams. And yeah, so that's the difference. Does that make sense?
Yep, thank you.
No problem. So are there any other questions about the test? If not, are there any questions or like topics you want to go over? We can do more about limiting reactant or like stoichiometry. Okay, 54. Okay, a mixture is prepared from 15 liters ammonia, 15 liters chlorine, measured at the same conditions. And it's asking, what is the volume of each gas when the reaction is completed? All right, so um, well, in this case, since we're working with gases and everything, we can just, so what do we have? 15 liters of ammonia. And what was our conversion factor again? For 1 mole NH3, how many liters of NH3 are there? Right, 22.4. Okay, so we start out with the same amount of ammonia and the same amount of chlorine gas. So how much, let's see how much chlorine would be needed. So for 1 mole, or for 2 moles NH3, we would need 3 moles of chlorine gas. But notice how in the end, we're going to end up multiplying by 22.4 again to get to liters. So we can just skip this step and just multiply by the molar ratio. So that's what's pretty great about working with liters. All we have to do is multiply by this ratio because we start dividing by 22.4, but at the end we multiply by it again to get to liters. So we can just skip this step. Okay, so Knowing that, we can do the exact same thing. We don't have to convert to moles because we're going to convert back to liters. What would be our limiting reactant? Would it be ammonia or would it be chlorine? If we divide by the coefficients, which one is going to be smaller? Right, it's for the chlorine gas, Cl2. So this is going to be our limiting reactant. So knowing that, we can go ahead and use our chlorine to see how much of everything we have left. Okay, so first of all, since we know that Cl2 is our limiting reactant, we know that it's going to be used up completely. So if it's going to be used up completely, then how many are going to be left at the end? Does the question make sense? So if we start off with however much of chlorine gas, we use all of it up, then how much is left at the end? If you have a cup of water and you drink all of the water in the cup, how much is left at the end? Does the question make sense? Oh, no problem. So if we start off with however much chlorine gas and it's the limiting reactant, so all of it is used up, how much is left by the end of the reaction? Yeah, none. So 0 liters. So it can't be A and it can't be E. So we have these 3 options to work with. All right. Next, how much ammonia is left? So we used up all of our chlorine. So to match that, how much NH3 was used up? So all we have to do is multiply by the ratio. So for every 3 things of chlorine, it's just 2 of NH3. So that gives us 10 liters. So 10 liters for every 15 liters Cl2, we would need 10 liters of NH3. So if we started with 15 liters of ammonia, how many are we left with? Yeah, 5. So from that, we can get rid of all the other answer choices, and our answer would be B. Does that make sense? Roy? Okay. Are there any other questions? Okay, so if there are no other questions on the test, then I can maybe go over some, I guess, review topics using the book. Is that okay?
Yep.
Oh wait, the one's like question 39. Mm-hmm. So do you want to solve more problems like this one? All right, so I'll check the book. All right, let me know once you can see the screen. Okay, cool. Stoichiometry. Mm. All right, looks like here I think we went over this already. Let me look for more limiting reactant stuff. Are you guys using Tro or Zumtol? Like for the book?
Shams online or something.
Do something like this. For 10.34, let's work on part A. So it's asking determine which reactant is present in excess and tell how many moles in excess it is. So do you think you can do something like that? All right, so to find the limiting reactant, what should we divide the number of moles by? Right, well, I guess to convert from grams to moles, we would divide, yeah, the coefficient, perfect. So for this one, so I'll just remember to divide the number of moles by the coefficient and then compare, see which one is smaller, and then you can easily find which one the limiting reactant is. So knowing that, which one is the limiting reactant? Right, it would be Cl2, and that's because all we have to do is divide by 2 in this case, divide by 1, and Cl2 is smaller, so that one is present. So knowing that Cl2 is our limiting reactant, which one is present in excess? Na, right? There are only 2 options, and if it's not Cl2, it has to be Na. Okay, so how many moles in excess is it? So this is asking us, how many moles extra do we have? So what we do is we take our limiting reactant, which we found was Cl2, right? 0.40 moles Cl2. And it's asking if this is the limiting reactant, then how much of sodium would we need to react completely with Cl2 if 1.20 is too much? So it's asking pretty much, how much would we need to use up both of them? And so what would we do? We just go ahead and use our equation. So what goes on the top and what goes on the bottom? Yeah, the coefficients. So 2 goes on the top, 1 goes on the bottom. We get 0.800 moles of Na. All right, cool. So if this is how much is needed to react completely with 0.40 moles, then how much is in excess, or how many moles in excess is it? Well, all we have to do is do 1.20 minus 0.800, and we get 0.40 moles in excess. If we check our answer, yep, makes sense. Okay, any last questions? Before we end for today?
Can you just like tell us the answer from like 1 to the rest? Like, can you just tell us the answer?
I think that might be uploaded later because I don't have the answers right now.
Oh wait, you don't have the answers?
I don't have the answers, but my dad can upload them later. He said he was going to upload them later.
Wait, when is gonna be later?
I don't know.
Alright, yeah. Thank you.
No problem. Thank you for coming, and good night.
Yeah, bye.
Bye.
Bye. Alright, thank you.
No problem.